Okay, so now let's look at this process in a little bit more detail. Okay, let me just change the color. So I will just draw the same thing, but only one van der Waals isotherm. I'm going to make it a little bit more exaggerated so that you get the detail right. So let's draw an isotherm below the critical temperature so that we will have a phase transition. Let's say it's like this. So as I said before, if you have your gas, you start compressing it, well, there will be a point in which it will naturally split into two phases. Okay, so you are coming this way until you reach this point that we called B before, and that's when your homogeneous system, the gas, will split into two phases and become heterogeneous. And these two phases, one liquid and one gas, are going to coexist at this pressure, which is the pressure I want to determine now. So I want to know what this pressure is. If you like, you can think of the gas as being described by this point here on the right hand side. So that's the state of the gas. And like I said before, the temperature and the pressure of the liquid is the same. But because the liquid is a lot more dense, it's represented by a different point in the VP plane, because there's a larger density, there is much lower molar volume for the liquid. So the liquid phase is characterized by this state here. And what happens as I keep compressing is that more and more of the gas is turned into liquid until everything is liquid. And when I compress further, compressing liquid is much harder than compressing gas, so that's why the pressure is rising so steeply there. Okay, so I will advance the result first, and then I will tell you why this is the case. The line where I have to cut, so this line of pressure equal to the saturation pressure, is such that it divides the isotherm into two areas which are exactly the same. So this area here is the same as this area there. The only line that can do that for a given isotherm is giving you the saturation pressure. So I do believe I didn't say the name before, or maybe I just said it in passing. I'm going to write it here because it's important. When you have this heterogeneous system where you have a little bit of liquid and a little bit of gas, and the gas is turned into liquid, this is called saturated vapor. Okay, that's the name of the system. It's a saturated vapor, and all gases are going to become saturated vapors if the temperature is below the critical temperature and if they are compressed sufficiently to change phase. Okay. I'm going to then use also the same notation I use in the lecture notes. So here I'm calling this point, just for reference later, I'm calling it C. This point I call it D. This is E. Well, I will put the E here. And as I was saying before, these states here, so states which have a pressure larger than the saturation pressure, are actually not forbidden. So these are states that can be realized, but they are very unstable. So if you manage to get your gas compressed very carefully in such a way that, it will visit these states up here, any perturbation is going to make it fall into this heterogeneous situation in which you have a liquid phase and a gas phase. So this part up here, this is again notation that I didn't say before. These states in this sort of hill here are called supersaturated, just because they have a pressure which is larger than the saturation pressure. Saturated. This is in the lecture notes. I didn't write explicitly the name of these states down here in the lecture notes, but I just tell you now, it's not important, okay? But these are called undercooled states. Undercooled states. Why undercooled? Because if you have a liquid and you manage to have a liquid at pressures, below the saturation pressure for that isotherm, well, it would look like it's really in a different isotherm of a lower temperature. Okay, what is happening really is that the liquid is in an unstable phase anyway. So let us think now that of a fictitious process in which we, compress the gas, it splits into two, and we turn all the gas into liquid. And once we are in this point, instead of continuing compressing, like I was drawing here, what I'm going to do is to try to visit the undercooled stage. Okay, so what I'm going to do is I'm going to, well, maybe remove this or move it a little bit down. No, that's not what I want to do. Let's move it like this. Okay, so what I'm going to do now is to start expanding extremely carefully my liquid in such a way that I visit the undercooled stage. I'm going to label this intermediate state here G. I continue doing that. All of these states are unstable, but let's suppose that somehow I'm able to experimentally visit all of them. My system somehow turns into gas in a non-sudden way, and I visit the supersaturated vapor range here, and I end up being in the same state B in which I started this cycle. So this defines a cycle. This is H, by the way, the state up here. Okay, so this defines a cycle. Okay, this is a cyclic process. Let's say what the process is: B to C, then to D, then to E, where really C, D, E is just meaning you're turning all the gas into liquid at constant saturation pressure. Then you arrive in F, you go to G, you go to D, you go to H, and you end up being in B again. Okay, so that's a cyclic process, and you can start over again if you're able to do it. Okay, this is not only a cyclic process, but it's also an isothermal process. Okay, so we know that in an isothermal process, the difference in free energy in that process with a minus sign is larger or equal than the work that the system can do on the environment. And we learned this 2 lectures ago in the lecture on thermodynamic potentials. So because the process I'm talking about here is a quasi-static process, I know that the equality here holds. So the work that the system can do is equal to the difference in free energy in the process. But the process is a cycle. So the difference in free energy is 0, because cyclic process, we have f of a minus f of a. Okay, so that's 0. So the work done by the system on the environment has to vanish. Okay, and we learned that if you have a reversible process, which is cyclic, the integral of minus p dv in the Vp representation is giving you the work done either by the system or on the system. You have to check the sign, but this area that I'm talking about is the area that I am now marking in this plot. Okay, so you see that the total area has to vanish. You see also that this bit up here is visited in the sort of clockwise direction, and this bit down there is in the counterclockwise direction. Is that right? Yes, this is clockwise, this is counterclockwise. In any case, you know the area of this part up here is going to have different sign from the area of that part there. And I know that they have to cancel exactly. So I arrive to the conclusion that the area down here, let's call it, I don't know, A1, has to be equal in magnitude than A2. And this is the same thing I said before. The line that defines the saturation pressure is such that it cuts the isotherm in 2 areas which are equal. Okay, so this result is a very beautiful geometric result, and Maxwell, again, James Clerk Maxwell, the usual one, arrived to it in its time. That was a really nice result. So this in particular, well, this has consequences which are important for us. And the first one is that you see you can geometrically determine the saturation pressure. So if I give you an isotherm, you can try your luck if you like, and you can see where do you have to cut to make the 2 areas equal. But this also says that while the system is in this saturated vapor stage, in which is split into 2 and so on and so forth, the pressure of the system is determined by the temperature, because if I give you an isotherm, you are able to determine this pressure. And if I give you a different isotherm, this pressure will be different. So the saturation pressure depends on temperature. Okay? But at the same time, I can choose, if I like to, the pressure and the temperature as my independent variables to describe everything. For instance, I could say, okay, fine, everything is now a function of pressure and temperature because I have a single component expansive systems and I have 2 thermodynamic degrees of freedom. So internal energy is a function of PT, and also G, the Gibbs potential, is PT, and also H is PT, and also the free energy is a function of P and T. Okay? But now what I'm telling you is that if you are undergoing this process of transformation between gas and liquid, you know that the pressure is fixed if you give the temperature. Okay? So what I'm saying is that there is a second constraint besides the equation of state, which is reducing 1 degree of freedom more. And now everything will depend only on temperature. Why? Because, well, the internal energy, yes, sure, it's a function of the pressure, but while the system is split into gas and liquid, its pressure is constant and determined exclusively by the temperature. Okay? So this is what happens in such cases. And you can say, well, the internal energy is a function of temperature. Okay? And we are not dealing with an ideal gas here. Okay? So that's another situation where the internal energy is truly a function of temperature. Same thing happens with Gibbs free energy and the enthalpy and the free energy and any other potential. You can define also the entropic potentials and so on. Okay, so that's one important consequence. When you are in the saturated situation, you are everything is really a function only of temperature. And let me see, well, there's another, if you like, nice consequence. I promised in the very beginning of the module that I will show you a situation in which you have a process which is quasi-static, and in this case isothermal, but irreversible. Okay, so to give you yet another example of processes that are properly and truly quasi-static in the ideal limit, if you like, theoretically, but still they are irreversible. And this is one of them. And the argument here goes like this. Okay, so let's focus on this process up here. So this little bit. Okay, imagine, okay, for a moment, that instead of considering, the entire kind of loop here, I consider a process which is simply, let me remove some things here to allow me to write. I only consider a process which is from B to C, and then D, and then H, and then B again. Okay, that cyclic process there. And then I think about it. Okay, so it's a quasi-static process. So I will write it. It's quasi-static. Yes, it is. It is cyclic. It sure is cyclic. Fine. And it's even isothermal. Why? Because I'm always sitting in an isotherm. Okay, so it's isothermal. Okay. So in this case, I know on the one hand that the difference in free energy should give me, because we're dealing with a quasi-static process, this difference in free energy, at most is going to give me the work done by the system, at most. And I know that my process is enclosing a positive area in the VP representation. And I know even I'm doing the cyclic process in the clockwise direction. So I know that I should be producing work. At the same time, I know I'm doing a cyclic process because I start and end in the same place. So the free energy difference is 0. So I won't be able to produce any work. At most, the work that I can produce is 0. However, this figure, this painting here there, is showing me a different picture. There is a non-zero area enclosed in this cyclic process. So then what is happening? Okay, because on the one hand, I know that there should be no work. And on the other hand, I know that if I do P dV and I integrate over the cyclic process B, C, D, H, B, I for sure get something less than 0. Not less or equal, less than 0. I get some finite amount of work. So now the trick here is that this object here, you can calculate that integral, but this is not equal to the work. So what we said in the very beginning of the module is that if you have a reversible infinitesimal process, the work is minus PdV. Okay? And then if you go and integrate that, over any cyclic process you want, like this, then you will get some work. And if this work is negative, it's work made on the environment, and so on and so forth. But this assumes that the process is reversible. And the process I'm talking about here is quasi-static, is cyclic, is isothermal, but is irreversible. Why is it irreversible? Well, let's just write reversible to be able to make a cross here. It's not reversible. So why is it not reversible? Let's have a look. Let's get things out of the way. If I go from B to D through C in this process, so if I take my system and I split it into two, I let it split into two, and I start turning the gas into liquid until I arrive to this point, it will be impossible for me to jump to the super saturated states. That is not possible. I can't do that. Because the state my system is in at the moment, which is this heterogeneous state of liquid and gas, is more stable than the unstable states in the supersaturated curve. So I won't ever be able to close this cycle. On the other hand, I can do it the other way around. So I can do it in reverse. I can take my gas, I can visit very carefully compressing it, all the supersaturated states, and at some point I can decide to shake it a little bit so that it splits into two. And then I start expanding it until it all becomes gas. So this way you can do the cycle, at least in principle, in theory, okay? But the other way around, it is impossible to go over the cycle. So this is an irreversible process. So the work is not minus PdV, and the area enclosed is not giving you the work done by the system in this case. Okay, so that's just one example to add to the list of processes with friction or processes with finite temperature differences, which may be quasi-static but non-reversible.